Alright, when June the 2nd. Let's do this. Sorry. Time needed to inform all employees. A company has n employees with a unique ID for each one from 0 to n-1. Each employee has one direct manager given in the manager array, where manager I is the direct manager of the ith employee. Manager head ID equals -1. Oh, hold on. The head of the company is the one with head ID. That's like the root. It's a guarantee that the subordination relationship have a tree structure. The head of the company wants to inform all the company employees of an urgent He will inform his direct subordinates, and they will inform their subordinates, and so on, until all employees know about the urgent news. The ith employee needs inform time I minutes to inform all of his direct subordinates. After inform time I minutes, all his direct subordinates can start spreading the news. There's a number of minutes needed to inform all employees about the urgent news. Okay, n employees, so they have unique IDs. Head ID, that was the root, and manager array, where the manager's I is the direct manager of the ith employee. So the ith employee is manager, okay, and manager head. Okay, that's fine. And inform time I to the ith employee needs this minutes to inform all his direct. Okay, so the first example we have the head of company is the only employee, so that's 0. This is a more realistic example. We have 2. Managers 0 is equal to everybody's 2, and inform time is 1, so it's going to be 1. So we want the number of minutes to inform everybody. BFS, okay, so in the first level it's going to be the root, and then we had these, right? So when we go through these, we need to find a maximum time. So we go through this, we go through the inform time, find the maximum, that's the current time. And then go to the next level, and we also need to find the maximum, right? Because you have to find the maximum until you hit the root. I think that shall be enough. Let's give this a shot. Okay, so we have a Q equals head ID, rest equals 0. And we say, while Q temp for ID I in Q, okay? For I in Q, oh, did you even do, sorry, I forgot. We need a, we need a graph. I forgot. Well, it's actually a tree, so we're gonna do tree. Okay, so we need to go manager, right? So for I am in enumerate manager, tree M is the manager, dot append I. Okay, and for I in Q, so it directly rest equals the maximum of rest and inform time I. And for am in tree I, not am for employees. Child. Right? Then temp.append child. Oh, hold a second. That's not right. The header company, hold on. They'll inform their subordinates and so on until all employees know about the urgent news. And they say he needs this man to inform all his direct subordinates. So in that case, hold a second. We have to keep track of the time. We have to keep track of the time. Sorry, that was not right. We have to keep track of the time. So we start with inform time head ID, right? And then this is not right. What does this append? Well, for I is actually we're going to say for manager and time in this, and for child in this dot append child, and it's going to be t plus inform time m. Okay, then we go to the next one, and we need to find also the largest value among all this level. That will be the, so we shall say res equals maximum res nt. Once we're done, q equals temp, and we'll return res. Okay, let's give this a shot. 1 0 minus 1 0 and 0. That's the first one. 6 2 2 2 minus 1 2 2 2. Oh, 0 0 1 0 0 0. Why do you always do this, man? 1. Okay, n head ID manager form time. N head ID manager inform time. Let's give this a shot. That shall be right. Try it. Wrong answer. Huh. Interesting. Expected 21. Huh? Okay, let's take a look. What did we get wrong? What's the test case? The boss is number 6. Okay. And 0 1 0 1 2 3 4 5 4 3 2 1 0. Holy crap. And then the time. This time is 1. The time is 2 3 4 5 6 0. So you should add all of these together, which is 21. That is bonkers. I only got 8. doesn't make any sense, huh? That's a fine. Let's just take a look. Let's take a look at the queue. Huh. I think the tree is wrong. Six to five, 5 to 4, 4 to 3, 3 to 1. No, the tree is correct. So it's 6. Yeah, 6, 1. 6, 3. Oh, 3T, 3M. 3M. That's interesting. I got 22. How'd you get 22? Okay, 6, 1, 5. Oh, we just start with 0, right? Just start with 0. Because I did it here already. There we go. Yeah, it was a typo. Unfortunate. Could have gotten this in first shot. Yeah, it was a little typo here. That should be right. Yeah. Wait, hold on. It didn't. I submitted, but interesting. Is that a bug? I think it's a bug. I think it's a bug. I solved it, but did not update. What does that mean? That's the end of the streak? Alright, we're gonna submit again and see what happens. Anyway, so BFS shall do. BFS is sufficient. When BFS, we can do DFS as well. Yeah, let's do DFS as well. Each level has to also record the number of minutes, right? The number of minutes passed so far for the current, so far for the current node. N plus V, no, E plus V. All right, let's try. DFS shall be the same. So we'll do this as the same. Def DFS. We have a node, and we have a time. Do we return anything? No. We don't return anything. We can return something. Okay, then we say we're a node. We want to know a node time. So from this going down, what is the maximum time, right? What is the maximum time? So rest equals to 0, right? So for child in tree node, DFS child, right? And T plus inform time, current node. This will give me the maximum time from here, right, going down. So I only need to find the maximum of this, right? So I think I just need to return the maximum of this. And we'll just return DFS head ID and 0. Wait, is that right? Empty sequence. If not tree node, return 0. That's not right. You know what? I don't think that's the way to go. I think I want to find the maximum, right? So this should be inform time node plus the maximum of going through all the children. Yep, that is right. I want to submit again. The runtime is NA. What? Dude, there's some weird things happening in this problem. Oh, this runtime's what? Is it too fast? Something is not right. Okay, something is not right. Yeah, something is not right. Anyway, DFS. Oh, it's the same. There's no recursion DFS. No, it has. From the root from leaf to the root. All right, I still don't know why this still have this issue. I have to keep an eye on this. It's not resolving for me. Let's see if I log out. Let's sign out. Let's sign out and sign in again. What was the original time? Okay, so let's go back to this. Okay, let's sign in again. There we go. You need to sign out and sign in again. Yep. A little bug, that's okay. Shortest path, okay, that's the yesterday's. BFS. Common edge. They do not check for the 2. Hold on, let's see. Number of edges from 0 to 3. Number of edges plus 1. Common edge. Node plus distance right plus 1. And read the code. So neighbors, if distance is equal to this, which means we haven't checked yet. So distance equal to 1 plus distance node. Parent, what's parent? Neighbor equal to node. Q.push. We set the parent node. If parent node is not equal to neighbor. Wait, so node's parent and neighbor not equal to node. Wait, hold on. What is this? This I understand. You're just incrementing, right? You're just incrementing on the distance from the root. And then this parent, you're telling me that the neighbor's parent is node. Okay, that's understandable. And I will push the neighbor in. And what's this? What's this syntax? It's a for loop and an else? So, wait, what? Anyway, the node's parent, the current node's parent is not equal to neighbor. And the neighbor's parent not equal to node. Huh? What does that mean? Well, what it means is at this point, so if we record everybody's parent, right? So 3's parent is 1, I mean, these are all good. So we come into 3 and 4, and we do 3 first. When we do 3 first, I'll set 1 to be 3's parent. And no, I'll set, because I'm looking at 4, right? I'm looking at 4. And 4, I get a distance. Okay, I have a distance for 4. And the parent, its parent becomes 3. So 3 becomes 4's parent. And I push 4 into the queue. Okay, so now we go to 4. Now we go to 4. And its distance already handled. We have a distance, so we don't do it. Then we will check parent node. So its parent is this. It's not equal to neighbor. That's true. It's not equal to neighbor. And its neighbor, I think, what is the neighbor at the current moment? It's not equal to node. Yeah, because I checked for 2 things. Apparently you only need to check for 1, but I... Let me think. You add 3, we'll push 4 into it, right? And then at 4, you will see that it's already in temp. So, yeah, that's no-go. That's a no-go. What if it's the other situation? Then we hit this, right? So I push this in, and so this one is in a queue, right? This one in the next queue, and now we're here, and this one's to push, and then now you cannot push because already something is in there. So I don't know. I don't like this one. Let's try this. Is the distance from root to I is the father, the parent of I. If 2 points met up, if 2 points met up and they are not father-son relation, they met in a cycle. If 2 points met up and they are not father-son relationship, they meet in a cycle. Distance cycle is smaller or equal than this. Okay. If 2 points, what do you mean 2 points meet up? What does that mean? 2 points meet up. Well, 2 points meet up means we have visited a node, right? If you think about this, this we haven't visited a node yet, so we give it its distance, and then we put it into the next queue. And then we say if this is not, which means this child has already, we already visited it. And then we visit again. Okay, that's when you visit again. So when you visit this same node again, you need to see I and j. So I and j is supposed to be parents, right? So I is supposed to be the parent of j, which means hold on. This is the father of I. 2 points meet up, which in this case is the j, right? Wait, hold on. The j. What we're saying is I will go to j, and this j has already been visited before by somebody else, or somebody else has come to it already, and now you visit it, right? So if you visit it, if the distance to I is the parent and the distance to j I don't understand. Let me draw it again. I don't understand. Do we have a... we'll just go... Right, we start from here. Distance is 0, okay? Now here distance is 1, right, at this level. And then we'll push this in, and this distance will be 2. And then we'll have this. This will also go to here. But then as j is equal to infinite. So now we say if this distance is smaller than this distance, then we say we have a cycle. Why? Why? Wait, what does that mean? That means you have somebody reaches a point and then you reach this point again. But what will be the situation where this is larger? It will be this distance plus this distance. Oh, I just realized. You can look at it this way, and this is the shared. Ooh, wait a second. But it still doesn't explain. What's this father-son? If 2 points meet up, talking about this and this, right? These 2 points meet up. Its father is this. Its father is this. And they're not father-son relationship. I mean, what it means if 2 points not really meet up, the 2 points are connected. If the 2 points are connected and they're not father-son relationship. So in this case, this is father is this, right? Its father is this. And these two meet up. But its father is this, right? So this is going to a node that has been visited before. And we'll check its father is not equal to this. Its father is not equal to this. That means these two are not encountered as, BFS. So this must have a cycle. So I return this plus 1. But the distance-wise, why distance I? So basically this is I, and this is J. And we are going from I to J and find out that these two meet each other. If they meet each other, and if they are, I still don't understand. I think a father's son is, the parent is easier to, okay, so this is 1, right? This is 1, this come here 2, this come here 2, right? And then, now this need to go to here, right? So its father is this, its father is this. So now this goes here, and then boom, we hit something, right? We hit something. That means this one has already been visited. So we have 2 nodes connected, and they have both been visited already. So we need to check, right? We need to check. So are they the relationship, a father-son relationship? And they're not a father-son relationship. Yeah, if they're equal. So what situation is I larger than J? I is larger than J. How is it even possible? I don't know. I don't know. I need a hold on. I need a case. I need to see, like, what is is wrong, but I want to see the case. I want to see why this is wrong. My God. This can already wait, what? Output 2, 2. The first output is 2. You gotta be kidding me. This is fine, this is fine. BFS, I, J. So this is 0, this is infinite. If it's infinite, this will become 1. BFS append. Next one, this is infinite, so that can be 1. That's fine. Now go back up. Okay, we'll go back up. I and BFS, I will be these two. Okay, so I is this. For J, oh, for I, so we hit here. And for J, in, this is already visited before. So visited before, then I say shall be I should be 1 plus 1 plus 1. Isn't this 3? What? Dude, this is bonkers, man. What the hell? What's my I? What's the J? And the distance. Yeah, let's not even do 7. Let's just do 3. Yeah, that's it. I just want to see. One zero. Wait a second. We start from 0, right? And then I go 1 1. Yeah, we start with 0 and 1 1. And then, oh, because in here, oh my God, it goes back. Lord, I only think you only want to go one direction, right? Doesn't make sense. Now it goes both directions. That's true. So from here, you go down. And then next one, you start from here. It can go here, or it can go here. It goes both ways. So you go here, it's been visited before, right? Therefore, if its distance is larger than this, that is good. Yeah, now it makes sense. Now it makes sense. Now it makes sense. Now it makes sense. So BFS from each node as a root. We keep track of the distance from a node to the root, right? if a node, right? If during BFS, a node has already been visited, we check whether its distance to root is smaller than the distance from the current node to the root. If it is smaller, right, then the already visited node must be a parent, which is allowed, which is okay, which is allowed. Otherwise, the already visited node is not a parent, which means we either have an edge connecting two peers or an edge connecting a child up to a different parent. That is the signal for a cycle. So when that happens, we simply add the distance of the current node to the distance of the already visited node and add one more, which is the edge connecting these two nodes. Now, since we BFS from each node, the first time that a cycle pops up, we can terminate the BFS. Okay, so we do this, and BFS, we have a root. What do we return? We return int, which is the smallest. Yeah, so we'll say return the smallest cycle size when starting at root. Okay, then I have a dists mass.inf times n. Oh, that's where we use n. And q equals root. Well, q temp for node in q. Right, for node in q. For child in graph node. If dists child is equal to mass.inf, right? Not visited yet, or visited, dists child equal to 1 plus dists node. Okay, and we say temp.append child. Elif dists child is larger or equal to dists node. The child is a peer or has been visited and it is not the node's parent. Right? If it's node's parent, the child will be smaller than distance. Right? So in this case, we can just return. Return what? Return dist's child plus dist's node plus 1. And then we'll return math.inf if nothing, right? So we can say for I in range n, we'll do BFS I, and we do, so rest will be the minimum of this. Or return rest if rest is smaller than math.inf, and also return -1. Okay, let's try. This is solution 3. Oh shoot. Forgot. Interesting. Hold up. Child. Right? Yeah, that's not right. What got wrong? Oh, you didn't set this root. That's why. This root shall equal to 0. There we go. Now we're good. Now we're good. Okay. Let's do this. Huh. Interesting. I think that's the one they're talking about, right? Oh, I think I know. You cannot. Yep. So I forgot if he changes method. You have to check every single one. Wait, did he check every single one? No, he did not. He did not. So this is not right. Yeah, this is not right. Yeah, you have to do this. Yep. Do I? It's all right. Okay, so that'll be it. Yeah, I'll end right here. All right.